Hello. Thank you for attending. I'll just start off first by handing this around, but I'll ask that you guys just handle the sides of this and have a look at it. And please don't drop it because they won't let me back in the building if it shatters. But this is a wafer with 16,800 radiators on it. Okay, and so each one of these rectangles that you can see on here is a speaker, 20 hertz to 20 kilohertz bandwidth. And what I'm going to talk about today is how we make these wafers into speakers. So you're welcome to have a look at that. And then we also have a booth here. If anyone's interested in hearing what sand sounds like, you could put the sand in your ears and listen to these silicon speakers. Hi guys. Oh, ASU, I remember you from yesterday.
Yep.
Yeah. You live in Tempe?
You did.
Oh, fantastic. I did as well for a little while.
Oh.
Yeah. Great. Yeah, just handle the wafer on the sides of the plastic as you're handling it, gentlemen, and then maybe you can grab it when they're done and bring it up for me. Thank you. Yeah, it's kind of fascinating. I like handing out the product so people can get an idea of what it looks like. Obviously, we laser dice the individual speakers into tiny micro speakers that can fit in earbuds. And so we call it solid state fidelity. And the reason we call it solid state fidelity is solid state electronics started at the inception of the semiconductor industry with the MOSFET produced to replace vacuum tubes in audio equipment. So solid state is kind of a term we use with amplifiers, tube amplifiers or solid state amplifiers. Now we actually have solid state speakers made out of this silicon manufacturing process. And so we call it piezo-MEMS, which is kind of a mouthful. Piezos for piezoelectric. And we use the inverse piezoelectric effect as the motor physics behind the work that's being done. It's also connected to a MEMS structure actually embedded underneath, and MEMS is micro electromechanical system. Again, another big acronym, but basically means that semiconductor manufacturing equipment can be re-engineered to make physical structures move at a micro level. So within this room right now, there's probably dozens of MEMS microphones. There's probably inertial measurement sensors and gyros in all of your phones or watches. And there's probably pressure sensors or gas sensors in this building. And there's ultrasonic sensors to know when there's no one in the room, so the lights get turned off. So there's MEMS sensors literally everywhere in our everyday life. So we've basically taken the MEMS manufacturing technology, mixed it with piezo thin films, embedded it, and created a solid state speaker. So what we're addressing with the first products are hearables, and we call hearables true wireless stereo earbuds, hearing aids, wired earbuds, headphones, and glasses. And you can even include something like goggles for VR and maybe gaming headsets as well. Hi. Oh, thank you very much. Appreciate it. Yeah, you could just put it there, plug it in when I need it a little bit later. Yeah, thank you very much. Yeah, we'll do it at the end. All right. Thanks for that. Thanks for the extra help. And so the company is a startup. We're a Silicon Valley startup in stealth mode for almost 3 years, developing the technology, and then June was our 1 year of being in production, so a little over maybe a year and 4 months that we've been in production with our flagship speaker and also our dedicated amplifier. Because it's a piezo system, it's voltage-based capacitive transduction and not inductive-based current transduction. So it's a different type of transducer, so we have to have voltage going in the thin film, which I'll detail in a following slide. And so basically we're just trying to look at the century-old voice coil. Voice coils have been around for a long time, and we figured out another way to actuate air and make sound. And a company founded by veterans from Apple and InvenSense, which is now owned by TDK, and it's a gyroscope company. Many of us had worked at Knowles doing MEMS microphones and balanced armature receivers, which are in headphones now and earbuds now all over the floor out there. And some other gentlemen from the team are from DSP Concepts, Qualcomm, and even NASA engineering. And so basically, we announced this in 2020, then we started producing and shipping in 2021, and we've got 61 patents granted worldwide, and over 100 patent applications still in process, and 33 of the US patents have already been granted, so the rest are international. And so we're developing not only these micro speakers, but we're also developing loudspeakers that work in air, right? So you would be able to hear this from across the room. We're also developing active venting. Many of you that use earplugs for any reason at work, or maybe if you go to a loud concert, you put earplugs in, as your voice gets louder. That's called occlusion, or occlusion effect of your self voice. So we have a vent that opens and closes, so you can put something in your ears to protect them, and if you want to hear the outside world, hit the button, the vent's open, and you can hear your outside world and then close them. So that's pretty cool, especially for singers. Anybody that's a musician here that's ever sang with in-ear monitors, you know that when you sing with in-ear monitors, your self voice is super loud, so your mix needs to come up in your ear to hear against your voice, or you back off on the mic. So we really like the active venting. And then also, since we can pump things, and we're small, we can do a lot of movement, we can do thermal management and heat dissipation by making these small little transducers embedded into electronic devices to push air in and out of a portable consumer electronics device. So there's really a lot of breadth and scope to the piezo MEMS technology, but what you hear at the booth today would be focused pretty much on earbuds. So for anybody not familiar, I've got a couple of slides just to break down how do you listen to sand. And so sand is around everywhere on the planet. Since we don't have magnets or copper coils, we don't have any rare earth elements to speak of in the manufacturing of this type of speaker, we start with sand. Well, how does sand become a semiconductor device? Well, sand is melted in a giant crucible at hundreds of degrees Kelvin, maybe even 1,000 degrees Kelvin, and they pull a single crystal of silicon out. Amorphous becomes into a single crystalline structure, and they pull it up with a press, and the thing will handle like 10 tons. So this is gigantic, and it's massive, and it's heavy. And so this gets sliced up by diamond saw to make little thin wafers that turn into computer chips and or speakers. And so this is kind of a rendering of the wire saw that would take that giant single crystalline structure. It used to be 1 inch in diameter in the 60s. In the 70s, they had 2-inch wafers. Then they quickly migrated to 4-inch wafers. In the 80s, they went from 4-inch wafers to 6-inch wafers. Then in the 90s, they went from 6-inch wafers to 8-inch wafers. And now we've got 12-inch wafers. So the single crystal silicon ingot can actually be 12 inches. We use an 8-inch manufacturing process. So once the silicon ingot is diced up, you get what you would call the wafer. And there's 25 wafers that fit in a lot or a boat that travels around by robots through the manufacturing fab. Once they have the wafer singulated, they can then dope this material. They can use photolithography to put patterns on it, and then put electrical conduction and or insulative materials and build up structures that turn into computer chips or any other kind of semiconductor device. We modify that process with the MEMS manufacturing so that we can actually move the structure and pump air. And so this is kind of a cross-sectional drawing, rendering basically, of say a wave file of audio. So we have an amplifier, this represents our amplifier, and it takes differential audio in or single-ended audio in. So we get our audio input from any source. And then what happens is we boost the voltage to plus or minus up to 30 volts peak to peak. And so what that does is it forces the PZT thin film to charge or energize. And then with the engineered stresses that we've put into the materials, we can deflect the silicon up or we can deflect it down. Now the interesting part about our voice coil elimination is that we have a complete coverage of the radiating surface area with our motor. So instead of a voice coil pushing at a smaller area of the diaphragm, 100% of the moving structure is surrounded underneath or covered underneath with PZT, and the PZT is the motor. So that means that the whole thing moves up and down with the electrical force, which is fairly interesting and goes to our listening test. When you hear over there, you're going to hear some interesting sound out of these speakers. There's no breakup. The diaphragm doesn't resonate. When it stops, it stops. When it's supposed to move, it moves. And anyone who's already heard this probably has heard really good, clear sound coming out of this technology. And so this is kind of a larger photograph of the wafer. And obviously you see some kind of 6-cell rectangles here. That's what you're going to listen to in the booth if you stop by. And so what does silicon offer over traditional speakers? And so this is our kind of feature wheel. Obviously, first and foremost, it's about sound. We can get really technical and talk about all kind of other technical things. But as a bass player and a musician myself and a sound engineer, it's really about the sound. And that speaks for itself when you listen. But the interesting thing for me is the phase. So where do we talk about phase on here? So The fast response allows us to react so immediately to the electrical input stimulus and also stop that we have a 2-degree phase shift from like 100 to 5K. And that's really, really good consistent phase. When you have 2 matched transducers in your ears, it's kind of like listening to 2 studio monitors that are perfectly matched in a good acoustic environment. So this is what we're going for with phase, is to have very tight phase, very fast response. And we'll show some slides in a little bit that kind of compare the speed of this transduction towards traditional speakers. Another thing that's pretty interesting is because of the manufacturing process, we're putting in our data sheets within 1.5 dB, but we're actually holding about 0.5 dB to under 1 dB of consistency. So a speaker off that wafer and a speaker off a wafer from 8 months ago and a speaker off the same wafer 8 months from now is going to be within 1 dB or less of each other in frequency response, total harmonic distortion, and sensitivity. So companies that make earbuds, they largely have to test what they buy and make sure that, okay, here's our A mix, here's our B mix, and here's our rejects. And they'll build matched transducers, but they have to test to match them. Not required with this technology. We actually record all of the performance characteristics of the device on a laser barcode on each chip, which I'll show in a couple of slides. And what else is important to mention here? Oh, IP58 rating. So this wafer can be dunked in water, salty water, muddy water, and if it's cleaned and dried off, it'll work. So it has passivation covering over it, so they're very robust. We drop test them from 6 feet on the granite slabs. We put them in ovens and bake them. We do salt and mist testing, so there's quite a bit of regimen for what we call reliability testing that goes into making sure the devices can survive out in the public domain. And the Japanese love this. This is a logo you may be familiar with. You'll see high-res audio on pretty much anything sold in Japan. And what that means is those products' extended frequency response goes beyond 20 kilohertz out to 40 kilohertz. And so since we have extended frequency response out to 80 kilohertz, we easily meet the Japanese high-resolution audio spec. So here's a look at the speaker after it's packaged. So the individual, the wafer is diced up to make individual die. The die is attached to a PCB substrate, and then we have a top port where the sound will come out of the top port, or we have a side radiator. So this slit here on the side might be difficult to see on the projector. The sound would come out longitudinally here, and you can see with the side fire, we can basically disappear into the shell of the earbud. Most earbuds have a shell to them, not even required with this technology, but if a customer of ours wanted to put other sensors or microphones or ANC into an earbud, we pretty much are out of the way. We have a small little output tube, and that's all that's required. And this is Montero, the speaker that we have at the table that you can hear. But we also have very small speakers, and these are really engineered for hearing aids or over-the-counter hearing health products. You can get 1 or 2 of those actually inside your ear canal, and a lot of companies are experimenting with those now. They still have full range sound, but they're just very, very, very small, and so the small form factor really enables them to be packaged for hearing aid. So this is the Montero Buds. This is what we have at the booth if you'd like to listen to it. And basically what's inside is a couple of tubes and an earwax guard and our speaker. It's 3D printed. This is not acoustically optimized material. It's not manufactured. We put these together ourselves and kind of glue them together and wire them up. So we're really just making what I would call a minimally functional device for people just to experience how does the transducer sound. And this is a little bit of a close-up of what we did to tune our frequency response. So the speaker itself has a lot of highs. It has flat bass response, and once you get to about 850, it starts to lift up. Once you get to 2, 4, 8, 10K, it starts doing this because the sensitivity increases over frequency. So that's pretty bizarre. You don't want to hear all this highs. You probably want to hear more lows or maybe a balance. So to actually create a balanced sound, we use microacoustics. And what we do here is we use a waveguide to shape the side port. We use this resonating tube, a smaller resonating tube, and then we insert that earwax guard. All 3 of those structures together will dampen the high frequency response that we have just with mechanical acoustics. We don't need any DSP to do that. So this is kind of witchcraft that not a lot of companies will teach you how to do. So we asked, Sony and JBL and all the likely suspects and all the IEM companies. No one wants to tell us how to do this, so we had to figure it out ourselves. So we failed our way into having a good sounding earbud on our own, And now we have this domain expertise, and we offer this to customers. We'll give the CAD away. You can have the mechanical drawings. We'll tell you the volume of what we've done. We'll even give you the COMSOL simulations to help you engineer your end product. So the frequency response, as I said, is flat all the way to about 850. Then we rise a little bit. And then we have this little bit of a peak here. We're just trying to kind of compensate for ear canal resonances. And then it kind of does its thing all the way out to 20K. The THD, or total harmonic distortion here, we'll see 4 drive levels. So we drove the earbuds at 48 millivolts RMS, which is very low out of, say, a headphone amplifier. And that makes our amplifier generate some voltage peak to peak, and that's this first shape. But you can see almost identical consistency in the behavior of the system as you drive up the volume. So it doesn't really change its sound signature from quiet to loud, which is pretty cool. And the other thing you see at the bottom of the THD is that we're, even at a level of 4.1 volts peak to peak, which is almost unlistenable because you're at 105 dB at 1K. You probably don't want to listen that loud. But even at that level, we're generating at 20 hertz 6% and at 2% at 20K. So that's pretty low distortion for that kind of volume. Most listening levels will occur somewhere around 80 to 90 dB, and you can see we're less than 1% all the way across, or slightly more than 1% all the way across. And it's just our first product. This is the first swing at the ball. So this is under development. We're refining these specs. We're making things better, but it's literally just the first attempt. And so what I wanted to do when I shaped the frequency response is I wanted to kind of follow the sound signature of a revered microphone in recording. So since music's recorded with microphones, mostly, and this Neumann U87 is probably in every recording studio worth its salt, you can see it's pretty flat, and then it has a little bump in the highs, depending on the polar pattern that you select on the microphone capsule. And so I figured, well, why not have something that was pretty flat and has a little bump in the highs? Right? If the microphone records the musical instruments we've been hearing since the 50s, why not have a speaker that can at least duplicate that accurately? So that way the source material that's recorded on your files and your tapes or your MP3s or whatever you're listening to will be accurately reproduced. So this was, my kind of attempt to get it close to the revered Neumann U87. And then I talked a little bit earlier about the amplifier that we have. So this is the amplifier. It's 2 millimeters square. It's tiny, and we're able to put it on the back of the speaker. So like a powered monitor for a recording studio, you can go to Best Buy or Guitar Center and get some Jbl Powered Monitors. Well, we make powered monitors here. And so these are giveaway development tools for companies to prototype with. We don't produce these in mass production because we're not an assembly house. We make the amp and we make the speaker, but we do offer these so customers can just wire up audio plus, audio minus, power, ground, and shutdown, and with 4 or 5 wires, they can start prototyping immediately. And then, like I said earlier, we give those away. And so what's different about this amp is it's Class H, and the Class H amplifier has 2 rails, a low power and a high power rail. High power rail is what gives us our voltage swing. And we only take, a small amount of power in, 3 volts is plenty, 2.5 on up. And we have a boost converter. So the boost converter boosts the input signal by 24 dB. So if 10 dB goes in, 34 dB comes out. So we get quite a bit of boost out of the amplifier, but we also generate V-bias. So like a studio microphone, you have 48 volts fan and power on most mixing boards, and that turns on studio mics. So this speaker needs some voltage applied to it to make sure it's flat, and that's called V-bias for us. So our amp provides the V-bias and the boost and the audio all in a very small, tiny chip that's surface mountable. And yeah, so this is in mass production now, and so with the Montero speaker, side fire, and top port, and the amplifier, those are our first products that we're shipping. So any questions from anybody so far? I'll stop here and just maybe take some questions if someone wants to know something or wants me to, dial in on something I spoke about earlier.
I have one. The anchor in the design of the driver, is that secret sauce, or what is the anchor like made out of?
Oh, it's silicon.
It's part of, okay.
Yeah, it's part of the silicon structure. Yeah, the metallization is applied on top of the silicon structure, but we use silicon everywhere we can.
Question.
Oh,
so
sure.
what moves to make the sound?
What moves?
Yeah.
We call it a membrane, And so you can see them here, but they're at rest. But when voltage is applied, they will obey the voltage. So if the signal goes up, we go up. If the signal comes down, the membrane goes down. So there's a physical moving structure. And I have an animation I can show you here that will give you what it looks like. Sure.
In the silicon, you see that every so often there are periodic darker areas in the wafer.
Oh, yeah, so that's a reject wafer. That's not a production wafer. And so those are probably test die or areas where we're experimenting with the laser to see how to ablate things out without fracturing stuff. And so that's just a kind of a giveaway stuff that we can frame up because we're not going to take a production wafer and bring it to a trade show. So that's just a reject. Yeah.
You mentioned that you're also looking into speakers.
Yes.
So for speakers, I'm assuming it's going to be a different design than that specific design that is going to be used for IEMs. So for are you going to mention later, or can you mention now? If not, what's going to be different?
Yes, I have a photograph to show the speaker that uses 16 of these in a tweeter array, but the loudspeaker technology is still in R&D, and that's not something that I have in the presentation, other than a hint something else is coming that works in free air with a similar approach. Just think if you could wire that whole thing up and have it on, something along those lines. Yeah. Thank you for good questions. I appreciate it. You look like a singer that I met down in Anaheim once, and I'm like, I wonder if that's the same singer that was in this band.
Wasn't me.
Well, obviously not. Pardon me for asking. So what I'm going to do in the next part of the slides is I'm going to talk about why they sound the way they sound. And obviously I hate talking about sound, so please forgive me. I hate this part because sound should be experienced with your ears, and I shouldn't be talking about them. So do not take my word for anything other than the technical aspects, and please come and listen for yourself. So a standard basic speaker we're all familiar with. It's been around a long time. It has several elements, 1, 2, 3, 4, 5, 6, 7 elements here. Some of them have 8, some of them have 5, but basically this represents a standard speaker. And we are hearing these types of speakers out on the show floor as dynamic drivers or balanced armatures, are called BAs. These are from the hearing aid space, but a lot of IEM companies use them. And there's also another company that uses MEMS called USound from Austria, and they have a MEMS actuator, which requires voltage to operate, but they still have 1, 2, 3, 4, 5, 6, 7, same structure, because they have a rubber surround that has to push the diaphragm back after the electrical force has moved it. So you have this spring and return force mechanism here, and that's expressed as a traditional coil-based or dynamic coil-based speaker. We all very familiar with this, but what we make is quite different. When you want to do a SPICE model, and a SPICE model in electrical engineering or electroacoustic engineering terms is how can I represent the elements of the speaker in electrical engineering terms of resistor, inductor, capacitor. So we have this RLC model, and this is something that can be put into modeling software. You can get frequency response outputs by changing the values of the different elements that make up these speakers. Someone asked about what moves. What moves is the silicon. And this is a console model, and this is showing with voltage applied that the silicon is going up and down. Now, each one of these 4 areas are represented here in the photograph. This is an actual picture. This is the cartoon rendering. This is the model, and this is the physical device. If you notice, it looks like the membrane is collapsed or concave. That's because there's no bias applied. I mentioned that we needed some V bias, and so once 10 volts of V bias is applied, that diaphragm comes to almost a planar operating state, and then once the sound comes in from the audio, it just goes up and down with the waveform of the music. No spring and return surround involved. No magnets, no coil motor, no mechanical tolerance stack up of is your voice coil in the center of the gap? Is your wire round, or is your wire a pentagon? You know, do you have air gap, and is it glued, and all that other stuff doesn't happen here at all. So with no rare earth elements, it's very earth friendly, it's very lightweight, passes all worldwide standards for safe products to put in and around your body. And so very interesting, very unique technology. And one thing I want you to pay attention to is the fact that you could see through this. And these are small, tiny slits that allow each one of those radiators to go up and down and not touch. Okay, so they have to have some bypass so they can move in air. And so that allows all of the radiators to have independent suspension. And that's important, and we'll talk about that in a following slide, why having air being able to come in and out of your ear canal is actually a benefit. So silicon is a very interesting material. It's very thin, it's very light, it's very stiff, and it's also very inexpensive and can be made in mass production. And so a lot of traditional drivers, you'll see this is a small dynamic driver taken out of a popular ANC headset, and we're scanning it with a laser system. And here is one of our speakers here. And you can see that this design is a little bit different. You only see 2 radiators here. Where's the 24 radiators? So this is our latest technology. This is a new type of MEMS, piezo MEMS transducer that we've developed that has more sensitivity. It actually moves a greater distance for the same input stimulus, and so it's actually able to move a greater distance as well. So in subwoofer world, car stereo guys may have heard the term xMAX. How far does your woofer move to pump bass? Well, this actually moves a lot further up and down as a larger structure than our smaller radiators. So we're getting a lot more bass, we're pumping a lot more signal with these types of designs. And obviously you see a very uniform behavior. You don't see a lot of anomalous buildup of reflections and thermal loading into the diaphragm material. So no breakup in this type of design. And so this is another rendering kind of showing a voice coil that's pushing up on a membrane system where the voice coil is attached to a very small cross-sectional area, and you have some vibration, you have some nonlinearities in the behavior of the system. Most people who make these speakers want this material to be as stiff as possible, but then it sounds too bright. So there's always this trade-off of constants that you have to work to make good sound. With us, obviously you can see through them, and they're going up and down independently. And you can see here that silicon rather, not silicone, sorry, is actually stiffer than a lot of these other materials people make tweeters out of and speakers out of. There's a lot of Kevlar used in drivers. Titanium, JBL's been famous for years for the TI series of titanium drivers. Aluminum, I had some bass cabinets from Hardkey back in the day that had aluminum speakers, pretty cool. Obviously paper is not very stiff, so on the Young's modulus chart, paper is very, very soft. Silicon's actually a pretty good material to make a speaker out of. And so I mentioned that you can see through here, and that we have obviously air passes by. So one of the things I noticed when I was tuning, so I was listening to these early earbuds, and I was putting AirPod Pros in, and some the new Sonys, and all the occluded earbuds, and some IEMs that I had bought for my band. And as I was listening, I can go about 20 minutes of listening to loud bass-heavy music with standard occluded earbuds and IEMs. But I was able to listen for like 45 minutes or an hour or more with our speakers, and I couldn't figure out why. I wasn't getting ear fatigue. So what's happening with sealed speakers, where you don't have a bypass of air in and out of the ear canal, is you're pressurizing your eardrum. Okay, you're trapping air inside there, especially if anyone's been to our booth, you know that we require a seal. So you put the Comply foam tips on, you seal them in, you make sure there's no sound coming in. Now you've got air in there. But because we were vented, we're actually able to move DC static pressure from against the eardrum out to the back volume of the earbud while you're pumping the bass. And so it doesn't affect the acoustics. You're listening to great, powerful bass. I play 5-string bass in a band. I'm pumping my bass, and I can do that for a 2-hour set, and my eardrums aren't pressurized because they're vented. So these speakers offer a really interesting, long-wearing, comfortable listening experience, which I haven't experienced before. So I think it's interesting if you guys come through. We have an EQ set up, and if you like bass-heavy music or upright bass or jazz or anything, come over there, play with the bass, pump the bass up, and you'll be able to hear really amazing bass, almost too much bass, but your eardrums aren't doing this. That's pretty cool. And so the Montero speaker I mentioned has a top port and a slot here to come out, for the sound to come out the side. And they have 2 different frequency response characteristics. You may recall earlier I was talking about how the sensitivity of this system increases over frequency, which is fairly unique, and you'll see that represented here. And the top port speaker gets pretty loud up there. That's 143 dB SPL. You don't want that in your ear, obviously. So For companies that want recording studio monitor quality, sound, and very accurate sound, the top port is the most resolving, but you've got to deal with that, amplitude. So like I showed in the mechanical design, different dampers, different tubes, different mechanical acoustics, and maybe some DSP would be necessary to bring that amplitude down, attenuate that down, and create your own target response. So, but look how flat it is, up to 850. I mean, all of our speakers are pretty flat, up to 850. So the bass range, the mid range is totally unaltered. The Sidefire actually does that for you, so that becomes a slot resonator, and it does bring things down above 7K, and so that makes it a little bit easier for DSP and mechanical acoustics to tune that high frequency, but both options are available and both are being used by certain companies. And what's interesting here is the SPL, so we can generate 112, 113 dB near 200 hertz, and at 20 hertz we're over 110 dBs. That's quite a bit of bass. And we actually EQ this, so if you come to the booth you'll see I have a bass shelf. I'm putting plus 14 dB at 40 hertz, which is for bass guitar. I have plus 12 dB at 63 hertz, which is the kick drum. So you can pump the bass on these if you want. But what's interesting about the bass being so flat and the low mids being so flat, where, drums and vocals and a lot of instruments are, is these resolve what's in the recording. If you don't EQ it and don't pump it up with the Harman curve and you just want accuracy, you got studio monitor flat. I mean, just inherent in the design. It's really, really nice. And then this here just kind of talks about the form factor. It's very thin, the amplifier is super tiny, the speakers are only 1 millimeter tall, they can disappear into the housing and leave all of this open for other sensors, bone conduction mics, it can take your temperature, all types of sensors can be embedded into a wearable or hearable, if you will. And then, there's just to show you the size of dynamic drivers and kind of a two-way setup with balanced armature receivers with a woofer BA and a tweeter BA and the PC board on the top. You can get an idea that we can produce the same type of response and the same sound pressure levels with a much smaller system. And I did mention we test these things like semiconductor devices. So we don't follow IEC specifications, we follow JEDEC. And JEDEC is the semiconductor industry standards for how you're doing reliability and lifetime testing. So we have a regimen of semiconductor related tests that we do. This is our burn-in board, this is hilarious. So this thing goes into an oven that thermal cycles up to like crazy temperatures with humidity. The reason they're on a circuit board is we apply the V-bias. We actually turn the damn things on to make sure that they could survive in Houston on your dashboard under the windshield while you're in the mall watching a movie, and then you jump into the air conditioning at home and nothing happens to the speaker. The sound doesn't change, it doesn't stop operating. So they're very stable. We've got very big customers having us buy $10,000 washers and dryers. And I don't know why, they say Whirlpool on them, looks like the same thing that's at Best Buy, but that's the one they make, that they want us to use. And we have to throw these in the wash with dirty clothes, wash them, dry them, and then they need to work. So that's that, then they do. Sometimes you'll get a failure from debris being stuck on it or residue from different detergents and soaps, and that's just kind of is what it is. But the fact that they survive that is astonishing to me. We also drop test them. We also do salt and mist and dust testing. Arizona fine sand is put into a chamber and it's tumbled around and made a mess, and then we ultrasonically clean them and they work again. So pretty interesting. Now, one of the biggest, many of the patents that we have are around how do you test this stuff. So this being a silicon wafer, if this wasn't a speaker, it'd be a standard electronic device. This would need to be tested. And there's a lot of machines out here called wafer probers, where you can have a probe card with little tiny fingers that touch the pads. You turn your device on and you send signal in, and then you have some other wires touching on the output, and you measure if your device is working before you chop it up and make a chip. So this is a first level test at the wafer probe, but no one really had an acoustic device at wafer sort before, and so we kind of developed our own intellectual property to have a specific type of testing at the wafer level. We also have very specific type of testing once the wafer has the devices singulated and placed into a package. Well, we better test it again. We better make sure that after it's in the semiconductor package and connected with the bond wires inside, that it's actually functional. So this is called a final tester. So wafer gets tested at wafer sort, and this is called back end or final test. And so we worked with a partner automatic system. So these are all over most manufacturing clients that package devices. So we found a company that we really like. We like their machines, and they're automated. And we worked with them, and we developed our own acoustic chamber. I mentioned earlier about the speaker. You had asked about a loudspeaker. And so what we did is we've taken, just kind of on a goof, we said, well, how many of these will it take to make a good tweeter? And so we kind of built some different arrays, and we made a little a holder, 3D printed, and it turns out that 16 top port Monteros make a really nice dipole, so sound comes out the front. But remember the back vent holes I showed you on the back of our substrate? We have those little holes. Well, sound comes out the back too. So we actually have a dipole response. This is the front, this is the back. Here's a little 3-inch woofer. It's in a basic 3D printed box, and we have a passive radiator on the back side of this. So you got a woofer here and a passive radiator in the back. And we turned them on, and we were floored with the sound. We've taken these to some of the world's most prestigious home audio speaker companies, and they were just scratching their heads. They were like, what the hell kind of alien technology are you bringing in here, Michael? And we're like, yeah, it works great. And then I was at NAMM show, which is a musical instrument trade show, happens in Anaheim, and I showed this to Dynaudio, I showed this to a couple other studio monitor companies, and they were just like, whoa, that's fantastic. We love this. So now we're starting to mess around with tweeter arrays with these things. And so I have a giveaway. I have like a little fun contest. So we're going to give a 32-bit, 384 kilohertz USB DAC away if someone can get close to the answer. And so if you want to take a guess at how many of our 20 hertz to 20 kilohertz piezo MEMS speakers are represented in this photograph, please take a guess. I'll give you a hint that the glasses Jim are wearing have some in there. I'm actually wearing a pair. I'm holding some of the speakers. I've already told you how many were in that, and I've already told you what was going on with the wafer. And hint, there's a photograph. So come to the booth and see me. Give me your number. Whoever's closest, I'll give you a little mini USB-C DAC. So I'll take some questions if anyone has some questions.